Hello, Matthews, Gatos here. In this video, we're going to cover infinite limit of exponential functions. Let's get started. First of all, I want to review for you a couple of exponential functions. The first one is where the base is greater than 1. So you can see all of these examples that I'm graphing, the base is greater than 1. Now, the first thing I notice is that all of these are increasing functions. And in fact, the bigger the base, the steeper the graph. Now, as I take my exponent x and I make it infinitely big, as x approaches infinity, you can see that all of these functions are going towards infinity. In fact, the limit as n approaches infinity of b to the n, where the base is greater than 1, actually does not exist because it doesn't approach a specific value. Let's look at another type where we have the base between 0 and 1. So you can see all of these base of the exponential functions are between 0 and 1. So again, on my graph, I notice that these are all decreasing functions. In fact, the smaller the base, the steeper the graph. So as I make x, my exponent, bigger and bigger, as it approaches positive infinity, this entire function goes towards a y value of 0. And in fact, we can say the limit as n approaches infinity of b to the n, when the base is in between 0 and 1, has a value of 0. Now we're talking about bases greater than 1 and less than 1. What happens when the base is actually equal to 1? So for example, the limit as n approaches infinity of r to the n, where r is 1. I think the easiest way of doing this is looking at it on a graph. So if I actually make my base 1 to the x, and I graph it, I get a horizontal line. The reason is because you're always multiplying by 1. And if you look in the table of values, regardless of what x is, your y value will always equal to 1. So the limit as n approaches infinity of r to the n will always equal 1 when the base is 1. Well, what about when the base is negative 1? Let's look at that. If I have the limit as n approaches infinity of r to the n, where I'm having, again, a negative base, I'm going to go to my graphing calculator. So I put this into my graphing calculator, negative 1 to the x. I press graph, and I don't get anything. Why is that? Let's go to our table of values. And you can see the value of x changes the value of y. It's oscillating between negative 1 and positive 1. So I see when my exponent is an odd number, the value of my power is going to be negative. Conversely, when the power is an even number, it's going to be positive. So it's going between positive and negative. And in fact, if I wanted to graph this, I would just have to zoom in. I did zoom decimal to get a tighter window setting. And you can see a whole bunch of dots there. They're not connected because this is not continuous function. So it's either going to be positive 1 or negative 1. So in this case, the limit as n approaches infinity of r to the n is equal to, does not exist when r is equal to negative 1. So we're going to now put this all together and try some questions based on these. When it comes to exponential limits, I really recommend that you guys do these graphically. So when I look at my first one here, limit as n approaches infinity of 2/3 to the n. First thing I look at is my base, and my base is a number between 0 and 1, which tells me I know I have a decreasing exponential function. So the limit as n approaches infinity of that is going to approach 0. Let's look at another one. In this one here, limit as n approaches infinity of 8/7. Now 8/7 is a number greater than 1. So I think about my graph. Graphs that have base greater than 1 are increasing exponential graphs. So the graph would look something like this. And I know when it's an increasing graph, as my exponent gets bigger and bigger, this limit grows without bound. So therefore, it does not exist. Let's try another one with a little bit of a twist. So this is the limit as n approaches infinity of 3 to the exponent of negative n. So first thing I want to do is I want to keep it positive. Let's write it with a positive exponent. So I'm going to rewrite this as the limit as n approaches infinity of 3 to the negative 1 all to the exponent of n. So I'm just trying to get at a negative out of my exponent. So then I'm going to rewrite this as the limit as n approaches infinity. Now 3 to the negative 1 is the same as the reciprocal of 3, which is 1 over 3. So now I have a base with a positive exponent. I see that my base is in between 0 and 1. So again, it's a decreasing exponential graph. And I know as n approaches infinity of decreasing exponential graphs, this whole limit goes towards 0. Okay, let's try another couple ones with some twists and turns here. So in this one here, I have the limit as n approaches infinity of an exponential function in the numerator and denominator. Now, my tip to you in this one is just to use our intuition. So I'm adding on a 12 and I'm adding on a 3. If I'm approaching infinity and I add on a 12 or a 3, it's really inconsequential. It's not going to have a big impact. So since I'm talking about an infinite limit, I don't have to worry about the plus 12 and plus 3. So I'm going to focus instead on the limit as n approaches infinity of 5 to the n and 5 to the n plus 1. So I'm just going to rewrite this using what I know about my rules of exponents, particularly in the denominator. I see that I have 5 to the n plus 1, which I know can be written as the reverse of the product rule. So when you have two bases with the same exponent and you multiply them, you keep the base the same and add the exponents. Well, if that's true, the converse is true as well. So I can see those cancel. So I'm left with the limit as n approaches infinity of 1 over 5. And I remember that the limit of a constant is the constant value itself. So I know this equals to 1 over 5. This one here, this is an application of exponential functions because of course a square root is the same as something raised to the 1/2. So very first tip I have, since I'm multiplying constant, very different than just adding a constant, making it 5 times bigger in the top, 2 times bigger in the bottom, I know based on my rules of limits, I can bring those constant values out front. So that's what I'm going to do. I'm going to rewrite it as 5/2 times the limit as n approaches infinity of the square root of n plus 3 over root n. So a couple of ways I can approach this. I think for me, the one that makes the most sense, I'm just going to write this as one big square root. And then I have the square root of a rational function. So I'm going to use what I know about rational functions. And remember that shortcut I used with rationals. I'm going to multiply it by 1 over n to the highest power, which in this case would just be 1 over n. So since I've done it to the numerator and denominator, it's fair. I haven't changed the question. So this is really 5/2 the limit as n approaches infinity of the square root of, now let's distribute this inside. So n times 1 over n plus 3 over n all over, multiplying those together, the n's cancel and I'm just left with 1. So what I really have is 5/2 the limit as n approaches infinity of the square root of 1 plus 3 over n. So this is a bottom-heavy function. So as n gets bigger and bigger on the denominator, this whole thing is going to go towards 0. So I know this is going to equal to 5/2 multiplied by the square root of 1, which is just 1. So this whole infinite limit just approaches a value of 5/2. In my last example here, I have fraction over a fraction. Of course, fractions are an application of exponents because fraction can be written as an exponent to the negative 1. I'm not going to do that in this question. What I am going to do is get rid of my fraction over a fraction by multiplying the numerator and denominator by the common denominator. So I'm going to multiply this to get rid of the fraction by an n and also a 3. Now, to be fair, I'll also multiply that by the denominator as well. So let's distribute that inside the brackets and see what our new limit looks like. So 1 over n times 3n is just 3. 3n times 1 over 3 is just n. All over, I'm going to leave that factored. So now I notice that in the numerator and denominator, I have same but opposite factor. So just to show that, I'm going to factor a negative 1 from my numerator so that my leading coefficient right here changes from being negative to positive. So negative n divided by negative 1 and 3 divided by negative 1. all over n minus 3 times 3n. So those, of course, cancel. And I'm left with the limit as n approaches infinity of negative 1 over 3n. Now, this is a bottom-heavy function. As n approaches infinity, that means that the denominator becomes infinitely bigger and bigger. Negative 1 over a really big number is going to approach a value of 0. So this whole limit has a value of 0. So this is a lesson on infinite limits. Of course, it brings to mind this famous mathematical parable, and it goes like this. An infinite number of mathematicians walk into a pub. First one says, "I'll have a pint, please." The second one says, "I'll have half a pint, please." The third one says, "I'll have a quarter of a pint, please." This continues over and over. The barman finally interrupts them, pours 2 pints, and said, "Folks, know your limits." I want to know why the barman said that. If you can make a comment in or tell your answer in the comments, I'd appreciate it. I'll let you know if you're onto something. So I hope this video helped. If it did, please give it a thumbs up and hit subscribe so I can help more mathies just like you. Thanks for watching, and I look forward to seeing you for the next one.